To start, I think. There's a couple of people missing, but they'll wander back in a minute. So the first part this morning was sort of a historical survey and a little bit of elementary accelerator stuff and entertaining, hopefully, and just gave you some sense of perspective of Daresbury and why we're here. The next talk, I want to get more contemporary. I want to look at what's going on now, and I want to look at areas of three challenges that exist. And I want to illustrate this with some real machines that are either in construction or in design or actually in operation at the moment. And once I've discussed these three frontiers, the energy frontier, the intensity frontier and the brightness frontier, at the very end I'd like to say something about present programmes here in the Cockcroft Institute and in the UK. There's a little bit of a brief summary at the last 5 minutes or so. Hopefully I'll be able to fit everything in. So we're going to start with the energy frontier. And of course the energy frontier will be different for electrons than from protons. Electrons are dominated by the synchron radiation. And the biggest machine that's ever built for electrons in the world is LEP. And here we are. Well, fancy that. We've seen it before, haven't we? People nowadays call this the LHC, but the tunnel was built for a different accelerator called LEP, which was even a different particle. LHC, of course, is protons. LEP is electrons. So this is a large electron-positron collider. Same picture as you've seen before. Big machine. Why so big? Because of that synchron radiation loss formula. The E you can't do anything about. You've got e to the fourth, but on the bottom you've got r squared. So the r squared term you want to get bigger and bigger. So you'd like a big radius. So you actually build this huge radius ring specifically to minimize the synchron radiation losses. Even such a huge ring as this at 27 kilometers, even that loses so much synchron radiation, it loses 3% of the total energy in one turn. So you can see there's a huge problem. This is 20 megawatts of synchron radiation emitted all the way around this ring. So you have to put 20 megawatts back in just to keep the energy constant without any acceleration at all. And this is such a challenge that the technology, as well as the civil engineering technology, have made two, I wouldn't say breakthroughs, but two very interesting solutions. First of all, the magnets themselves are so low field that the very low field itself gives you problems of quality and control of how you make such a low field. 0.1 Tesla is actually quite low for an accelerator magnet. And so they built some rather revolutionary magnets where the magnets were a sandwich of metal, steel and concrete. And most of the magnet is concrete. So it's you can imagine a concrete magnet with laminations intermittently through it, providing the 0.1 Tesla. Quite a difficult task. So these were quite unusual magnets. 3,000 of them, to give you some idea of scale. Big machine. And the other problem, of course, is to get this sort of this RF power into the beam. And this was done with superconducting RF systems. Superconducting RF systems have been a bit slower to be developed than magnets. I mean, superconducting magnets have been around for a long time. Most of you will have come across a superconducting magnet at some point, perhaps in your lives already. And they're not novel in that sense. I mean, people try to get better and better magnets, but they're not a novel breakthrough. Superconducting RF really has only been around for 20 to 25 years maybe, but much shorter than superconducting magnets. And generally we'll use niobium as the material of choice of the cavities. Sometimes the cavities will be made out of niobium itself. Sometimes they will be made out of copper coated with niobium. And because of the skin depth effect, the field is only in the niobium, whereas the copper is just a substrate which allows you to build the structure to give you the acceleration. 288 cavities are built in LEP. Here's an example of a radio frequency cavity in LEP. Big thing, as you can see. And there are 288 of them. Here they are in blow-up. Here's a structure. You can see this is a typical source of RF structure with a number of cells, one behind the other, multi-cell cavity. You can see it in model view in here. Many challenges, much challenges. Power saving is only one issue. I mean, they are very effective compared with conventional powers. They also tend to be higher quality. So you tend to get less problem with these instabilities introduced by errors in the cavity in general. But they do have a few problems. I mean, they're particularly sensitive to microphonic. What that means is if there's any vibration anywhere in the system, it tends to destroy the quality of the superconducting field. They're particularly sensitive to vibration. So you have to have good shielded, mechanically shielded laboratories. The other thing you'll notice is all this stuff. Suddenly we're in a world like semiconductors where people have to dress up and put headgear on and put clothes on, and it's not a very pleasant working environment to be in, I'm afraid, for those people who have to do this. These are the technicians generally who have to assemble things. because you have to be absolutely clean. Any sort of dust and contamination will wreck your system. There are now processing systems in place here at Daresbury for many of these systems, many of these types of systems. We don't have any way of machining niobium, but we do have all the cleaning systems are in place. The preparation, surface preparation systems here available. This is just an amusing aside, what you get with a big machine like LEP. It's amazing the things that affect the accelerator. Here, for example, are the change of beam energy measurable in the machine in 1992 due to the tide coming in and out. Now, where's the tide? We're in Geneva. The tide is where? 1,000 kilometers away. So the tide from the Atlantic Ocean hitting Europe is detectable in Geneva on the accelerator, believe it or not. And the other thing they had big problems with when they first commissioned it, they didn't understand for about 6 months. They used to get these intermittent interference with the machine, even to being made unusable. And eventually some bright spark managed to phase it and time it with the TGV, the train system, which is a few kilometers away going past, sucked energy out of the Earth system. So the Earth loops somehow interacted back with the magnets in this big machine and were very observable. Quite incredible really when you think about it. But it just shows you how sensitive a modern accelerator is. So that was electrons. Now what about protons? Well, we're all into this now, aren't we? LHC, everybody's heard of LHC. What limits the proton energy? Well, generally the size of the machine. The 27, in other words, you get magnets as high as you can. It's the challenge now of superconducting magnet technology, not RF. It's not the RF problem now, it's actually bending such high energy machines, beams. The system uses niobium titanium. This cable is used all over the world. It was invented here in the UK at RAL in the 1960s. And you can see here is an example of a modern magnet. It doesn't look much like a magnet you've probably come across before. Nearly all of this is mechanical stability. What you find with a superconducting magnet is if you get any sort of movement in the magnet, it destroys the superconducting state by having some sort of energy dissipation which gets magnified in the core. So the beam goes in here, and then here are the coils, and the coils are shaped with different current densities in them to produce this perhaps uniform magnetic field across the aperture in the middle. So this is not a random distribution, it's a very carefully worked out harmonic distribution of coils to drive the field in a dipole magnet of this sort. The Tevatron was the first big machine. This is the US machine world record holder before the LHC took over a short time ago. In 1987, the Tevatron reached, as it says, 1 TeV for the first time, was the energy record, using 4.2 Tesla dipoles. Now the LHC now has operated at 4.8 Tesla, so it's gone beyond the Tevatron in the US. But that is only 4 TeV. And as you all know, I'll say something more about this in a moment. The reason it's 4 TeV is because there's been problems with the LHC. Eventually, it will run up to 7 TeV in the beam, which will go to 8 Tesla, which is almost double what we've reached so far. The cryogenic cooling systems, the liquid helium for these superconducting magnets is absolutely enormous. Tens of kilowatts and huge amounts of helium within the system. Just a few pictures for you to look at. Here's a dipole magnet. Believe it or not, it's straight, of course, because the bending radius is so small, it's so large, excuse me, that you can have a straight magnet and you don't see the difference. The actual chord difference you see is very small. So you don't have to build curved bending magnets. The curvature doesn't show up in just such a short length. Here's the tunnel. Can't see any curvature, can you? And here is the incident that happened in 2008, shortly after commissioning the machine, the first few weeks after commissioning the machine in 2008. Gosh, it's 6 years ago since this happened now. And this was a huge problem. I mean, this took a year just to replace the damaged components. There was an explosion in effect. There was a leakage of, there was a collapse, a spark and an explosion. Fortunately, there was no personnel were in the tunnel, or there might have been actual fatalities. It was such a violent explosion. And 59 magnets were damaged, many of them replaced, and 2.4 kilometers of beam vacuum pipe had to be replaced. All this took a year to do. And even now, of course, we're not back to the full, as I've mentioned already, the full spec. So it restarted a year later. Collisions of this half energy, 50% of full energy we're at now at 3.5, were in March 2010, but that was already a world record for energy. So we've reached the energy frontier at that point, 4 years ago. The Higgs candidate was first discovered 2 years later, and has been confirmed only 2 or 3 months ago. that it's the particular Higgs that was being looked for. And in February 2013, another shutdown, 2-year shutdown. What was it for? To repair the problem from 2008, which was never fully repaired. It was only partially repaired, sufficient to allow them to run at half energy. So there's a sort of hidden tail in there, actually. But fortunately for CERN and its reputation, the Higgs came out with the half energy. Otherwise, it would have been a lot more criticism of what went on, I suppose. So what actually happened is their safety officials would not allow them to run at full energy with the present CERN, the present LHC setup. So they've taken 2 years, and from next January, I think it's January they'll come on the air again. They will be able to run in principle at full energy. It's not yet been demonstrated, of course, but there's nothing stops them in terms of safety analysis. Early 2015, possibly. There are still already talks about upgrading the LHC. I mean, we talk about what the next machine is, but the next machine will almost certainly be the LHC upgraded into a different state, possibly sometime in the 2020s, which some of you may end up working on, because already we're looking at the luminosity challenge of dynamics within the LHC, and people are looking at new machines. This is an example of LHC with an electron ring added onto it, so you can do EP, electron-proton collisions, which somebody would like to do. But I actually suspect this will never be built, because it's a minority interest. There is a powerful scientific case for it, but if it's going to cost billions of pounds or dollars or euros, it's unlikely to proceed, I think, unless it was a mainstream case, which I doubt it. But this high luminosity version, which will rebuild LHC in a different format, is at least more likely to happen, but not for another 10 or 15 years. But you need to understand it takes 10 or 15 years or 20 years even sometimes of design work to produce a real machine. So you might find yourself working on something for a long time. Now let's switch back to electrons. So how do we get over this problem of the synchron radiation? Well, we stop bending the magnets. We go back to linear accelerators. A LINAC, of course, has no such synchron radiation loss because it's not subject. The acceleration in the LINAC of energy increase is much, much less. The dominant effect of synchron radiation accelerating of charge is going around the curve, going in a curve, which is why the R squared term appears. So if you take the R squared term to infinity, the synchron radiation is negligible. Here's an example of a modern alternative. You do an electron source, you do a damping ring to get it down to a small size with that synchron radiation damping I already mentioned. We haven't got time to go into, but you'll deal with in your lectures later on. And you put it through the main LINAC, and you have another similar system on the other side, and you have head-on collisions. And these system here might well be 20 kilometers in total length. These are huge systems to go to TeV type energies, but that's what's being sought, a TeV electron beam now. And they may or may not have separate surface tunnels. And there's something called the ILC, International Linear Collider, that this Cockcroft Institute was heavily involved in from the start, 10 years ago. A lot of design work has been done on that, which I'll explain in a minute. I'm not going to go through these parameters here. I just wanted to pick one of them out because there's lots of really challenging parameters here. You could spend the whole lecture talking about this one slide. Look at this one here. We talked about nanometer beams. So the proposal is to build an electron accelerator which will be running at hundreds and hundreds of GeV, which has a vertical beam size of 6 nanometers. How on earth do you deal with that? A 6 nanometer beam? It's frightening. But it has to be done, and a way will be found to do with it, I'm confident. There are various techniques where you can indirectly look at the beam size in another part of the lattice and correct it in a sort of indirect manner. But how do you get 6 nanometer beams to collide? You know, you got say 10 kilometers producing one 6 nanometer and another one. How do you get them to collide? Very difficult. But of course, what they actually do is you scan through them in some way and have something which would depend on detecting something as you get them corrected, and some feedback system will come in and do it. These LINACs again are superconducting, as you would imagine maybe with these systems. Here's an example of the mainstream cavity design. There are 9 cells, I think, in there, and this has now gone up to 1.3 GHz. Remember I mentioned 500 megahertz? Well, these are smaller structures. As the frequency goes up, the dimension of the structure gets smaller and more handleable. This is made of niobium, machined. These are what the cells look like. These are actually some different, slightly different types, so you can see the design changes a little. See, each of them has their own properties. The finishing and polishing of these things determines the field gradient. If you can get to 35 megavolt per meter, which is the aim of this work, then you get a 40 kilometers in other words 20 plus 20, which I mentioned before. The whole system is 40 kilometers long, which is already huge. And you've got a lot of RF units, you've got a lot of cryomodules, and you've got a lot of cavities. So these cavities here, you've got to make 15,000 of those. I mean, even that, just that fact alone, just that one project, can you imagine how much industrial requirement you have to produce these sort of things? These things can take, well, many days to produce, because you've got to make them, you've got to weld them, and then you've got to prepare the surface preparation. You've got to do all this sort of chemical polishing and electropolishing to get the discharges out of the system. So this is a fantastic task. Here's another number that you might want to reflect on in these environmentally conscious days. The RF system requires 250 megawatts. That's average power. So we're into accelerators which need their own power station, aren't we? When you've got these sort of numbers. Now, maybe the world will tolerate it, but you can imagine the arguments you're going to have to go through as an accelerator community to justify these sort of levels of power. The greatest challenge, we talked about challenges. Well, maybe the greatest challenge is the cost. Here's an example of this machine costed. And this is where the costs go. And you can see nearly all the costs go in the LINAC. LINAC completely dominates the cost of the project. All these other things are all other bits of the source which are almost irrelevant to the argument. And you can see here we're talking about, now, history teaches us these figures will almost certainly go up, not down. I'm afraid it's just a fact of life. As you study in more and more detail, you find more and more requirements are needed, even to meet your original spec. It's a very difficult thing for physicists, this, because you're required at some point to make a promise to the funding agency that you can build things for the price you've quoted. And if you just throw in arbitrary contingency, they'll throw it out. You can't say, well, we want another 20% because things we haven't even discovered yet will just suddenly appear because this is revolutionary stuff, which it is, that nobody's ever done before. So these are frightening numbers. I think you'd agree, $8 billion. But it's not impossible. $8 billion. I mean, it will be a world machine. So Europe might well want to provide a third of that. USA might give a third. Asia with Japan and Korea and other, China might want to give a third. Or maybe the Chinese would build it as a labour cost, which is factor 3 lower than the European or Western ones. There's all these arguments about where they would go. That's just a bit of fun, really, to show you that you don't have to have circular machines. You can have a machine which is almost circular. You can have a racetrack machine, as these are called. And look at this one. This is called a dog bone accelerator for obvious reasons. Why would you build a ring like this? Well, you build a ring like this so it fits mostly, because it's very, very long, kilometres long perhaps. It fits within a narrow tunnel. And so the civil engineering cost is much less than trying to build a big circular ring. So these are things which are studied by people, which are rather unusual. So I'll just show you that. And that ILC design at the moment is being parked. I mean, there's a design study document that was produced about 4 years ago. CERN have an alternative scheme, which they pursued on their own separately from the ILC design, which I've just shown you, which requires this rather revolutionary idea that you have two beams. You have a drive beam, and the drive beam goes along in parallel to the, so here's the drive beam. The drive beam is very, very high currents, but relatively low energy, few GeV. The drive beam actually just pushes energy from its own self into the adjacent structure of the high energy ring, the high energy LINAC rather, the high energy machine. So this is a two beam accelerator. It's like a transformer, if you like. So you get energy across from a low energy high current beam into a high energy low current beam, which is what you would do in a transformer. The main beam is 1 amp. 9 GeV is the starting point, and 1.5 GeV as an example of a solution. This has been studied in this sort of period at Click, and this now would go up 30 gigahertz. Now we've gone to a huge frequency where the components are now little small things that you can hold in your hand. A 30 gigahertz structure, it's only a few centimeters across. You can literally pick it up in your hand. And they have done tests on this, and they've broken the world record. This is the world record for the accelerating gradient in a convention. This is not plasma. This is a structure, a metal structure, has been shown to be able to support this sort of accelerating field, which is great. But unfortunately, they've had lots and lots of problems with breakdowns. I mean electrical breakdowns, high voltage breakdowns. And so they've now made a decision about 3 or 4 years ago to go to more of an intermediate frequency. This will come down. You won't get that at this frequency. This decision was made about 3 or 4 years ago. So they're now concentrating everything around this frequency, which is still small by normal accelerator standards, but not quite as small as they'd hoped. A few parameters again, but this was at the original 30 gigahertz thing. But you can see the overall length of the accelerator here. If you go to 1 TeV, it's 7 kilometers. If you go to 3 TeV, which some people would hope for, it's now 33 kilometers. These are huge still. So it's not obvious what the solution is to this. And just coming back to that RMS beam size again, you know, here was the 3 nanometers buried in here somewhere. And these are the things that have been built already. Very challenging, very, very challenging. Just to summarize briefly for you the activities in the UK. These are all things which people within this institute have worked on. Every single one of those topics. These are major topics that have gone on in the last 5, 6, 7 years, since about 2000, actually 10 years, 2004 or 5, the work really started. So, superconducting undulators, targets, Linux structures, a lot of RF stuff has been done, a lot of optics stuff, collimation, damage studies, how to collimate the beam, how to control beam loss, crab systems, that's about how you twist the beam, because if you're not head on, which these systems tend not to be head on, they tend to be at an angle for each other. The bunch has to be rotated so it slides through itself in a maximum efficiency. A lot of work here, particularly at Lancaster, on these systems. Feedback control, machine ID. These have been supported by Research Council grants from STFC and all the PPARC when it existed, the previous Research Council, and European Union. There's large European Union money now flowing into accelerator work, which is encouraging at least. The European Union recognise this work is very important in a number of big grants to international collaborations. So that's the energy frontier. That's the first of the 3 topics. Now I'm talking about the intensity frontier. And this is basically about protons. The brightness frontier will be about electrons. I'll come back to that in a few minutes. So high power proton accelerators, HPPA is the abbreviation. Lots of applications. The energies usually are not particularly dramatic compared to what you've just been hearing about. But the beam current, the intensity, is the big issue. And one of the biggest issues of all with the proton machines of high intensity is the losses, because the losses are very damaging. They're particularly damaging to structures. If you get even a small loss with a very high intensity beam, you might be making components highly radioactive, for example. You might be making them unusual, you might be destroying their properties. There's no radiation emission to worry about, which is good. The other problem you've got is at intermediate energies, hundreds of MeV, even GeV, the protons are probably already energetic enough that space charge isn't a problem. Now, if you do remember, you go back to a basic physics textbook, space charge goes to 0 as you go to a fully relativistic beam. A fully relativistic beam has no space charge problems internally. However, a low energy beam, which is non-relativistic, which you have to inject at initially from a gun, say, has huge problems with space charge interaction. So you can't get high density of proton bunches at low energy. So if you want a high density, what you have to do is produce the protons at low density and at some later point squeeze them into a higher density structure, which is what's normally done with these systems. Well, one example, and one big example of very high intensity proton machines, is spallation sources, i.e. neutron sources. Neutron sources using spallation reaction. And here's the example of the national source, which has been at RAL now since 20 years, 30 years ago. Wow, 30 years. And this is, as I say, a modest energy at the moment. Here's the synchrotron with a LINAC, and there are 2 targets. One was the original target, push the protons into. So the proton goes into the target, interacts with spallation interaction and produces with high cross section a neutron beam. The neutrons tend to be high energy, so they generally have to be moderated down to lower energy for the experiments. So the target itself becomes absolutely huge. And this is that plots to that. So there's the ring. You see sort of you can see the circle there. And here's the first target in here. So you see how big the building is for the target and experiments. And here's a relatively new target station, which was opened 5 years ago. I can't remember, 3, 4, 5 years. Anyway, relatively recently, target station 2. And ICIS has claims and could claim to be the most powerful neutron generator in the world and the most intense proton source in the world, bar one example, which I'll show you in a minute, which they never talk about. So here's just this is just showing the LINAC. Here's one of these Alvarez type structures with these things there in the field. You can see all the way down here. So that's the LINAC. Here's an RF system. This, I think, is the full synchrotron, 800 MeV, so the curvature is quite noticeable. You see it now, the curvature. And here's a plan view of the target, a photographic view of the target. So I've already mentioned this in my earlier talk. You know, this was, you've seen this picture already, the Cockcroft-Walton set. And here is the replacement, which was done in 2008, I think I said, by the RFQ, which is I won't go into, I've got time to go into it. It's a particular type of specialized accelerator. What are the upgrade possibilities of the most powerful one in the world? Well, the upgrade, well, here's the RAL site. I'm going to talk about Diamond in a few moments. Here is ISIS. Here are the two targets. The orientation's changed a bit. Here's the new one. Here's the old one. And you could take the beam from this synchrotron, 800 MeV, feed it across the path here into a new synchrotron, which is about 4 times higher energy. Immediately the power goes up by a factor of 4 because it scales linear with the energy. It's an energy current product. It's the power in the system. So power goes up by a factor of 4. But in fact, at a 3 GeV synchrotron, you can probably get at least a factor of 2 more current in it. It'd be easier to do with higher energy. And so you can imagine quite a substantial increase, perhaps not an order of magnitude, but getting on that way as an upgrade on the site. Whether this will ever be built, I don't know. These plans have been worked on for about 5 or 10 years, and I'll explain another possible place for the funds in a moment. There's the world record holder. So now this is the most powerful accelerator ever built in terms of average power, 1.2 megawatts. And that's a lot of power. That's average power in the beam. I mean, how do you dissipate? Where do you put it? It's got to go somewhere, that megawatt, even if it goes into a target or into a beam stop. Already it's a challenge. But it's not very high energy, of course. So you can stop the beam quite quickly. But you may not want to stop it quickly, because if you've got a low energy beam with a lot of power and you stop it quickly, you dump very, very high power density into what's stopping it. You'd actually like to stop it over a longer distance if you can, stretch it out a bit. Less efficient stopping power, in other words. Anyway, that's just an example of a different machine which is used mainly for nuclear physics and some medicine. This is the SNS project at Oak Ridge, which is the next generation neutron source, which took over from RAL about 3 years ago as the most powerful source in the world. Its spec is 1 megawatt, and I think they reached 1 megawatt about 3 years ago. I know they've reached 1.4 megawatt this year, but that is the most they'll ever get, and they won't run routinely at 1.4 megawatts. And that's a 1 GeV system with a compressor ring to get the pulse length correct. The target is made of mercury. There's a lot of debate about what the best target is to produce neutrons. It's a combination of the nuclear physics properties for cross sections and everything, and also the dissipation of heat and power, which, as you can imagine, mercury perhaps is easier to take away. Superconducting structure in it as well. This is Europe's answer. For a long time, very controversial project in the UK, because of course the UK, a lot of people wanted to put the money into upgrading ISIS. The alternative is to not upgrade ISIS, perhaps, and join a European project for a brand new project. You can imagine all the politics involved in this decision. The UK announced about 4 months ago that it will join the project. The project was approved for construction about 4 weeks ago. So this is the latest big accelerator project in the world, European installation. I don't know how many of you are fans of The Killing or the Swedish detective things. Are you also a fan of The Bridge? If you've seen The Bridge, there it is. See that? That's the bridge. That's the bridge between Sweden and Denmark. So that place up there is Malmo, and that place over there is Copenhagen. The bridge goes between the two, and this is Lund, which is about, as you can see, about 10 or 20 kilometers away from the bridge. And this is a major signal radiation site, which is now this is the new neutron source is going to be built here. And this will be the new synchrotron for signal radiation. So the Swedes have got huge investment now. Sorry, I should have just pointed this out. Now this frightens the hell out of a lot of people in this country. I don't know whether this is achievable. 5 megawatts is a big jump from 1 megawatt, which is the world record at the moment. More or less 1 megawatt anyway. And the UK will commit 165 million over presumably about 5 years, 6 years. So it's not all in 1 year. And this is interesting. It will commit it in kind. What does that mean? It means you're not going to give anybody any money. You're going to take some part of the project, and you build it and you deliver it back to the project owners. This is quite a popular proposal nowadays with big projects, to give people a bit of a sort of encouragement to join the project. Well, join us, make your contribution, but make it from your own resources. So you've got your own people working on this, and you've got your own investment going on. And it's quite popular. But you can imagine if you've done a big design study and you've costed it, you've made some assumptions before you got approval. You've made some assumptions in the costing, haven't you? What have you assumed? You haven't assumed that the British will make certain components in kind. You just costed it, presumably with some common cost basis. And I don't think anybody's really solved this problem. What does it imply, this? How do you make sure that it really is 165 million that the UK is putting in? It may not be, maybe 120 million to the UK. Do you mind? Do you say, well, that's fine, you know, we've saved some money, we've got it built, what we want? We can imagine the politics of this in-kind thing is quite dramatic at times. The other area, which, coming back to particle physics again, which high intensity protons and high power beams are needed, is the neutrino factory. This is just a concept idea for you if you haven't come across it before. So this is a device that will produce a huge amount of neutrinos for neutrino physics. And the device starts with a proton beam, which is accelerated to some particular energy. In this particular example, 15 GeV. RCS means rapid cycling synchrotron. So it's a synchrotron, it's just a conventional ring. You go into a target and you produce pions. So the protons convert to pions in the target. The pions then are produced output and drift. And as they drift, they decay into muons. So you get proton to pion to muon. And the muons have to be cooled, sort of absorbed, if you like, into a high density structure because they fill a rather big space, cooled down and injected into their own linac to get them up to high energy. So the variety of accelerators take them up to perhaps, there's debate about this, but perhaps 50 GeV. And the 50 GeV muons are now in this ring, and here's an example of a muon storage ring. That's a funny shape, isn't it? Why is it that shape? It's that shape because the muons decay into neutrinos. Lifetime at non-relativistic lifetime is 2 microseconds. Obviously the lifetime gets better as you go to higher energy. 50 GeV is much longer. But these things will decay, and they'll decay right the way around the circumference. They'll be decaying as they go around. It's nothing to do with what's in the machine. They decay independently of the track that they're on. It's nothing to do with bending them or focusing them. It's just their natural decay rate statistically. So you want long stretches that can add up into one direction. So that whole decays from this corner to this corner all come down this line. So in this particular case, there's 3 possible lines. And these machines are usually built with the muon storage ring vertically at some point, so that the line goes through the Earth. Because remember, neutrinos don't interact hardly at all. You can go 1,000 kilometers through the Earth without any problem at all with a neutrino. And so the idea is not to go along to surface level, but you can actually go and cut through the Earth to another country, or perhaps even on the other side of the Earth, where your experiment is measured. It's quite a mind-boggling concept, actually. The design studies of this have been led more or less from the UK in the last 10 years. These universities here are the ones who've led the way mostly. You can see there's one Cockcroft sort of leading figure in there. Design funding since 2004. Studies have been done. Drivers, neuron accelerators, blah, blah, blah. And European Union support is significant as well. Our mice, I'm going to tell you what mice is in a minute. Just let me sort of complete the latest. This is the latest design concept. It's a bit different than what it was before, but not really. So there are proton accelerators at the front end here. Maybe a linac, maybe a synchrotron, maybe an FFAG, different type of cyclotron. They will come together at some point into some decision, which will then bombard a Mercury target, probably Mercury. Again, there's some debate about this. Remember, Mercury was used in some spallation sources as well. Bunch will be manipulated into some multiple sets of rings. Look how complex this is. Several sets of rings, 3 or 4 here to get the thing up. Eventually, after accelerating through several accelerators, the muons will go into the final. Now, it's not that triangle any longer, it's now a racetrack, but for the same reason, the racetrack has a long straight. So as you go along here, all these decays along here all add up and go along this line. And as you can see at the moment, there are 2 of these rings, and this is a much smaller scale compared with what the particle physics ones we've been looking at before. This is only a mile or so, 1.5 kilometers across. So this could fit in perhaps interesting places, like RAL, for example. So here are the challenges of Neutrino Factory. These sort of power levels are even bigger than the spallation source. Now I raised my eyebrows at the 5 megawatts. Remember, we've only achieved 1 megawatt so far. So you're asking the project designers to go an order of magnitude up on what's been achieved so far. And of course you'd like to deliver, because you'd say this is a generational change. And if you're not delivering an order of magnitude upgrade on what you've had before, well, should you be spending hundreds of millions of pounds? So you do need to promise some major upgrade. But really, this is technically tremendously challenging, the 5 megawatts, never mind the 10 megawatts. The survival of the target, can that target cope with this sort of power levels going into it? Can you capture the muons and cool them? Can you accelerate the muons and store them? Well, the designers believe the answer is yes. So all I can say to you is you may find yourself working on this project at some point. Very interesting project, still very much design study, still not clear what its priority is in the particle physics world. But it may be that after we've exhausted LHC, that neutrino physics becomes a focus for worldwide attention. If you have some of the arguments that are had about how it may solve, for example, the matter-antimatter asymmetry. Where's all the antimatter gone? And that might be one example of something which you wanted a neutrino experiment for. How do you cool these muons? They're like electrons, but they're heavy electrons, so they're very non-relativistic. So the synchronous radiation emission is negligible because their mass is much higher than the mass of an electron. So you don't get the advantage of electron. So another idea for cooling is that you send these devices through an absorber, and the absorber takes energy out of the device, and you then put the energy back in again with radio frequency cavities interlaced with absorbers. So here's an absorber, here's a radio frequency accelerating cavity. So you end up having to traverse this structure, getting all your energy back again. Because the new energy, if I can put it that way, has been put in a parallel line by the fields, the off-axis component is relatively smaller because the on-axis has gone up and the off-axis hasn't at all, because you don't put any energy in transversely. So using this technique, it's believed you can damp the cross-section of a muon beam. This will be tried out at RAL, but after many years, this system is not quite operational yet. But a beam line has been built from ISIS, extracting protons and into a target. Pions come out, pions decay into muons quite quickly, very quickly in fact, and then traverse this muon beam line into mice, which is in this area here. Just to show you that actually exists. Just a couple of other points before we leave high intensity machines frontier. This is a Japanese answer to some of the questions. And this is an interesting example where they combine together many applications. So they've got materials and life sciences, they've got a spallation source, they've got a particle physics source, they've got quite a high energy, 50 GeV, they can do neutrino driven, they can do all sorts of things. So you can do this. You can have a lot of fun designing multi-user, multi-application devices. But I have to say you, the politics is horrendous. I know from personal experience of what happened when they tried to combine particle physics sources with synchrotron light sources, and the arguments about scheduling and who has priority and how you give them priority if they've suddenly got a new result and all that sort of thing. So a lot of the funding agencies have got a little bit sort of cautious about multiple users, but the Japanese still seem to think they can do it. And maybe in Japanese culture you can, I don't know. And a couple of the other things you can do with high power protons. This is a topic of considerable interest to the Cochrane Institute. Was pushed quite a bit by Manchester and more latterly by Huddersfield University, who've sort of taken over a lot of the work. Can we build an accelerator-driven nuclear power station? If we can, then this might be very attractive for several reasons, one of which would be that it's fail-safe. The accelerator will be the reactor core will be subcritical until you add the neutrons from the accelerator. If you switch the accelerator off, the core immediately goes subcritical. So if you like, you're built-in safe from that sort of problem. This is very attractive to people. You might well want to do some muon physics with some high-power protons. I don't think these people will ever get their dedicated muon source because frankly, it's too expensive for a narrow interest group to justify. And then there's therapy, cancer therapy. We've all seen these pictures in the paper about the little child who's gone off to have proton therapy in Czechoslovakia, is it? Czechoslovakia. Is it Czechoslovakia or is it Poland? I can't remember which it is now. Anyway, you probably all saw the story 2 or 3 weeks ago. And there is no significant proton therapy in the UK. Now, the Bragg peak from protons is shown in this red one. This is the argument. The argument is that you put protons into human tissue and the energy loss is very low until the end of the track. And once the energy has gone reasonably low, it all gets dumped in one spot, compared with, say, photon or neutron or proton therapy, where you get continuously deposition so that the organs before and after the organ you're aiming at get a lot of irradiation, particularly damaging for children. There's only one proton therapy unit in the UK, and that's close to here at Clatterbridge, about 20 miles away, for those of you who don't know where Clatterbridge is, up on the Wirral. And they are limited to low energy. And the only cancers they can treat are eye cancers, where you don't need much energy to get into an eye. So they can't do any generalized cancer treatment. The UK, after years of prevarication, has decided to build 2 new proton therapy centres. One in the south of England, which I think will be, I've forgotten who's building it now, one of the London universities, maybe Imperial, can't remember, no, University College, I think. Anyway, the point is there's going to be one in London, there's going to be one in Manchester. And this thing is probably will be a commercially bought system, unfortunately. But at least it will reawaken interest in perhaps accelerated developments and next generation replacements and all that sort of thing. So maybe you'll find yourself, some of you in the room, working on advanced proton therapy machines in the next 5-10 years. And that is the collaboration, coming back to the nuclear physics fission driver, spallation neutrons driving thorium. Thorium is very popular with people because it seems to be less threat from weapons terrorists, if you make it thorium, whereas lots of power stations with uranium in are sort of seen as a weak link in the fighting against terrorism. And a last slide, I think, on this topic, reliability. Now, if you're ever going to build a power station, it's got to be reliable, hasn't it? And one of the problems we've found already, which people don't talk about too much, but I'll share this graph with you. This is a real graph using real data. It's a slightly unusual graph. Along the bottom here is the length of a trip. In other words, your accelerator is running and then it trips off. How long before you get beam again? And that's given us a graph along here, from 0.1 of a second up to 1 million seconds. These are real data points, and this tells you the number of trips per day, which are at least as long as that. At least as long as the trip length. And you can see this graph here. This is quite a damaging graph because this tells you that basically we're nowhere near a system where you could actually offer this to commercial enterprise or a health enterprise. Just nowhere near. The machines trip off. They trip off sometimes for short periods, yes, very frequently. Lots of times a day they trip off. Many times an hour, typically. You barely notice it because they're off perhaps for a fraction of a second. Maybe you only notice something where the trip is off for tens of seconds. But for example, if you're irradiating a human patient, you can't afford unknown trip lengths, can you? Everybody who goes and gets proton therapy at the moment, whatever the newspapers say about the poor little child who's gone off to get therapy in Eastern Europe, it's a highly risky process. It's not a well-developed process yet. And a lot of work's got to be done to make it that way, if we really believe in it. Anyway, enough of that topic. I want to go on to the third topic now, which is brightness. And the brightness refers to the electron beams which produce radiation. To get bright radiation, you need a bright electron beam. Almost sounds intuitively obvious. So the brightness is the flux coming off divided by the emittance. That's this area of this density, if you like, of the electron beam we discussed earlier on. And the emittance of a synchrotron storage ring scales in this way. So if you go to high energy, the emittance gets bigger. That is the result of the synchrotron radiation emission. The synchrotron radiation emission is a noise term. It shakes the beam up and tends to make the beam bigger in a storage ring, the equilibriums. The number of cells here helps you. If you can build a big ring with lots of cells, you can get back to a smaller beam. That's buried away in the detail. You have to believe me on that. So if we compare the original SRS here, 2 GeV, 16 cells, 100 nanometer radians. The European light source, which replaced it 10 years ago, goes to higher energy because it wants to reach higher X-ray energies, and would be even worse at sector effect. It's gone to 32 cells, which helps enormously. There's a bit more than that to its comparison as well, but just to illustrate to you. The old idea of these bending magnet sources I showed you earlier on the SRS is gone. Nobody uses synchronous radiation from a bending magnet any longer. People want brighter beams, so they go to these multiple arrays of magnets which wiggle the beam as you go through them or down the straight section. And you either have some incoherent addition, so the output is just n times the output from one pole comes from n poles, or you can get some coherent interference phenomenon. And in that case, you get a huge increase, because now you've got, of course, coherent emission, where the radiation emission is proportional to the square of the beam intensity, not linearly. There's the European light source. Here's a couple of rivers. Remember I mentioned about foundations? And this is basically a riverbed this stuff is designed on. This is Europe's, possibly the world's leading light source. And this is in Grenoble. And there's a high flux beam reactor, by the way, if those who are interested. Neutrons. This is a comparison of what are called third generation synchrotrons. The first generation of synchrotrons used that awful loss of radiation, which pained the particle physicists, and went parasitically and used it by building little exploratory stations. Second generation was like the SRS, dedicated to synchron light source, built from the start for synchron radiation. The third generation used these undulators, these wigglers that wiggle the beam and base their output completely on that. So that's what this third generation means. And here is the world record holders. Here's the lowest emittance. Here's Diamond, which I'm now going to tell you about briefly, which is the UK's response. So there's Diamond. Hey, that looks a bit like SRS, doesn't it? A LINAC, a booster, and a storage ring. Same sort of concept. Going up to 3 GeV rather than 2 GeV now. Quite a big circumference. Big straights that you can put these special magnets into that I've just mentioned. There's the lattice. Here's your double bend achromat. This is a real machine now with a real design of that, like that lattice I showed you before. So the blue things are the quadrupoles, and there are also sextupoles in this lattice which are corrected for, as you can see. It seemed to work. Stop working. 168 sextupoles around the ring. So they've had to overcome those dynamic aperture problems, dynamic stability problems I showed you earlier on. Here's Diamond. Here's the gun, the starter electron gun. Here's the LINAC. There's the booster. I think that's the booster in there. And here's the storage ring, 3 GeV ring. You see a bit of curvature. And here's Diamond sitting at the RAL site. What happened there? Diamond is now a fairly mature machine. It's been running for 5, 6, 7, 8 years, but there's still accelerated physics studies done on it, and still interesting accelerated physics studies, because there are different modes of operation that are still of interest, which haven't been completely overcome yet. Top-up is very important now. I've shown you those beam lifetime things before. The users don't like beam lifetime losses, not just because they have to go away for a couple of hours while you refill the ring once a day, but also during the decay, the thermal load on the optical components varies as the beam starts to come out. The users would really like a flat beam to keep thermal stability to a very high level. So what you do to overcome that is you fill the ring full of beam, and the major beam is filled at perhaps once a day. And then for the rest of the day, you every few seconds tickle the beam up with a little bit more. You inject a tiny amount, perhaps every few minutes. And that keeps the beam level to within that loss within a few minutes, not over 10 or 20 hours. So that's been done. It's been done at Diamond, and they've looked at coupling between, I talked about coupling between the horizontal and vertical planes. They've managed to overcome some of the coupling issues and get very, very small vertical emittance, 2 picometers. I think that's a world record actually. Non-linear dynamic studies have been done, collective effect. There's a lot of things still to do on Diamond. And if you get the chance to spend some time on Diamond, I even think we should be thinking a bit more about sending some of you down for a week or two just to work on Diamond, just to get some experience of synchrotron. Nevertheless, third generation light sources based on storage ring have some fundamental limits, which are not going to be easy to overcome. And I've already mentioned how the radiation emission shakes the beam up and stops you getting to very, very tiny beams, cross sections. And even if you did get to tiny cross sections, the scattering of the electrons off each other within this very tiny cross section would reduce the lifetime, would cause losses in the beam. And there's all sorts of other restrictions. So there's fundamental limitations. So about 7 or 8 years ago, some of us here decided we would look at the alternative, which is called an energy recovery LINAC. So we go back to LINACs, because the problem with LINACs is you couldn't get the current in LINAC. You can't get the power you can get in a synchrotron. So here is an example of energy recovery. You inject from the injector into the LINAC, into your experiment. Most of the electrodes don't interact, go through, round, back here, round this ring, and you re-inject them into the LINAC. And this time you re-inject them 180 degrees out of phase. Remember that very first bunching discussion we had this morning? If you're at the wrong phase, it slows down instead of speeding up, or it decreases energy. So it works as a sort of decelerator. So you decelerate the beam back, all the way back to the same energy as the injector energy was originally, and dump it. And you keep doing this. And now, because of this slowing this down, the energy from the electron goes into the structure. So you're getting your energy for free, if you like, not for free exactly, but you're getting most of the recovery, most of the energy you've put in originally. So now you can go to much more powerful systems. This led us to build a system up in the tower, which some of you, how many have seen Alice? Have you all seen Alice? Not so many yet. You should make sure we see it while you're here at some point. So here is a real example. This is a drawing layout. Here's the gun. Here's an injector superconducting accelerator. Feeds into the main ring, another LINAC. Around the ring, there's a bunch compressor system here, which allows you to get very short bunches for experiments. There's a wiggler that allows you to use free electron laser, which I'll talk about in a moment. And round and back again. When you get to here, 180 degrees out of phase, you make sure that you've changed by half a wavelength as you go around one orbit, and you decelerate and dump. That's exactly the equivalent. It's a green machine, energy recovery. And we think you can get sub-picosecond pulses if you do it well. So ALICE stands for Accelerators and Lasers in Combined Experiments. So it's got many applications, but it's an accelerator physics project, basically, that was built for us. And here's an example of more of a cartoon. I'll tell you about this in a minute, Emma. Uses the same injector. It uses the same sort of LINAC structure as those ILC ones. It's not a coincidence. People here have worked on both projects. There's a photograph, slightly distorted. Here's the gun. This is the first accelerating structure. It's actually been moved out of the way to get some access when this photograph was taken. This should really be in line on here. It's a bit confusing. Beamline, lots of quadrupoles in red, dipoles in blue. Double bend achromat. Look at this. Here you are. Here's the two dipoles, and here's the central quadrupole. That double bend achromat solution we discussed with you before. This injects into the main ring here, round that ring, all the way round and back again. Here's the loop, and here's the beam dump actually back down here again. All this is power supplies and cryogenics and stuff in there. Very crowded. And this is just to prove that energy recovery works. In fact, here is the main demand on the RF system. When you phase everything correctly, it works. We've run an FEL. I'll talk about FELs, Compton backscattering, variety of applications I'll leave you to absorb. Just a quick diversion for 2 minutes on Emma. This is a revolutionary project funded for DARSRE in March 2007, and here is the Emma ring. Now you can't actually see easily on this one, I'll show you on the next time, but there are no bending magnets in Emma. This is the only accelerator, circular accelerator in the world history that's been built without bending magnets. How do you get the bending? You go in a focusing magnet and you go off center. So the whole beam is moved off center in the current. So now just rather than the beam being centered and off axis particles oscillating, the whole beam moves off and is steered by the off axis effect of the quadrupole on the beam. There are still F&D quadrupoles, of course. Small project. Money's now run out, so we're funding it from our own resources in Cockcroft and Aztec. And here's a few blocks showing it. And this requires, because of this off-axis movement, to change the focusing and bending of the machine and change the energy in the machine, you have to slide the quadrupoles on sliders in and out of the ring, have them adjustable all the way through. So it's a very, very unusual, interesting project. It's up there. You're going to go and have a look at it. Its experiments are underway. I've not got time to deal with them in detail, but you find out that these are extreme beam dynamics differences compared with the synchrotron. And a lot of studies are going on it. So we're looking at many of these topics. Here's some beam. It shows you the size of Emma. It's injected from ALICE. Here's F quad and D quad in cavity. Here's some losses with no RF. It's all. I haven't got time to go into it in detail, but you've got a picture of that in your handouts. You'll absorb it, I think, more readily then. So the last topic on brightness is, where do we go next? We've had third generation. What is fourth generation? Well, fourth generation, by common agreement, is coherent emission. And here's a standard laser diagram. Okay, you've got pump and you've got a gain medium and you've got mirrors, and the thing goes backwards and forwards and it grows up to some power level, and eventually some power level is taken out through the mirrors by one mechanism or another. Can we do the same sort of thing without the material gain medium? Because what we know about conventional lasers is that although they have tremendously good properties, and the medium includes solids, liquids and gases, and apparently quite high powers and short pulses, there are some problems straight away because you can't extend into the extreme ultraviolet or X-ray region because you haven't got any medium that will laze at those sort of energies. You can't tune the energy much. You can tune them a little bit, lasers, but not very much. And of course, the power level output is limited by the fact that that medium there can only absorb so much power before it stops functioning. So the answer is to replace the medium with a free electron laser interaction, an electron wave energy exchange. So you set up a system whereby you transfer energy. Each pass of the particles, there is an energy transfer process, just as there is in a gain medium. So it becomes the gain medium itself, and the gain medium is a magnetic field, in effect, rather than a material. And you can control that, and you can build a system where instead of now being incoherent, you can actually get a coherent output, which produces fourth generation output from highly bunched electrons in that system. Now there's the basic system again of an FEL. So again, we have a gain medium in the middle, which in this case is an undulator magnet. The electrons are injected in. The electrons go out again. The radiation is trapped between the mirrors, and just like in a normal laser, builds up gradually to higher and higher rate. And the output wavelength, I won't go into this, but you'll do this in one of your talks, one of your lectures, I think, the undulator wavelength equation. So that's an oscillator because it's a bit trapped in a cavity. And in the infrared region, they've operated for a long time now. Tunable high power, very successful user experiments. Tried to get to higher energy by going to storage rings of higher energy. Not terribly successful, but Cockcroft people were involved in a project funded by the European Union, again, where the EU comes from, and this was the world record. So for an oscillator system with mirrors, the world record is about 190 nanometers. Why? Because to get less than 190 nanometers, your mirrors don't work anymore. These are dielectric mirrors with multiple coatings on them, designed specifically for short wavelengths, and they run out of steam at about 160, 170 nanometers. So fourth generation light sources will have to look for something else. What do they come up with? Well, they come up with an amplifier instead of an oscillator. So this is a variation. So on this particular system, the electrons only transit once. You use one group of electrons, you have a single pass, the radiation builds up all the way through this undulator. These undulators are very long, tens of meters typically. So we've got big magnetic structures now, a long interaction region. And you get some radiation out, but you need kiloamps in your electron beam, it turns out. There's the world record, was done in 2009. I think it's still the world record. This was built in Berkeley, California, and has reached 1.5 angstrom. The undulator length you can see is about 50 or 60 meters. So this is the interaction region. So this is a magnet, 50, 60 meters long, in which the interaction takes place. The energy is 14 GeV. This uses the LINAC, which has been used for particle physics for 40 years. Just use it for another purpose. So inbuilt ready-made injector. We have an answer to this for the UK, and at this laboratory in this building, all of this has been designed. It's called the Next Light Source for the UK. And this conceptual design study has been completed. It is available. You can read it yourself. It's probably in the library somewhere next door if you haven't got a copy already. It relies on a superconducting LINAC. All of this has been analysed. It's 2 GeV in magnitude. It's got several free electron lasers on it. And this could be the next level of generation of light source for the UK. Nothing anywhere else in the world as similar to this has been produced. The CDR in 2010 was produced. The answer was there's no money. put it to one side and come back to it in 5 years. 5 years is up next year. So next year I would expect some sort of realistic response to, do we start looking at this again? Do we throw it away? Do we start modifying it? Is it right for us? And the sort of beam dynamic studies that have been done by people in this building include trying to preserve the bunch length flat to 150 nanoseconds with various properties. I haven't got time to go into all these, but again, you can read them in your slide package. They give you the properties of the beam as you make your way through the pulse, which is femtosecond scale along the bottom here. Energy spread, emittance, various properties evolve. The last thing I want to talk about now in this last 5 or 10 minutes is test sources. So we've looked at all these various accelerators which now exist. We've looked at the studies that have been made of new generation. We've looked at frontiers. What are we actually doing here now? What would you actually join in and help to take forward? Well, before we move on to Daresbury, I'd just like to mention there is another test stand at RAL. It's called the front end test stand, and it's the upstream end, the starting point of a high intensity proton project. In other words, you could plug anything you like on at high energy. It might be spallation source, it might be one of these energy amplifier things for power station, it might be anything. But the idea is to study the properties of the beam at relatively low energy. And that is in place at RAL and being added to, as we speak, various upgrades. And again, it's worth having a look, if you get a chance to go to RAL sometime, having a look in at that system. What are we doing here at Daresbury? Well, some of you may or may not have heard of this project called VELA, Versatile Electron Linear Accelerator. This project was built with money given by, believe it or not, the Prime Minister when he visited the site 4 years ago, 3 years ago, whenever it was, where are we, 3 years ago, 17th of August 2011. He came here and he made a speech about investment for industry and about how Cockcroft Institute, in effect, and the Daresbury Lab could help industry. So they gave us £10 million, more or less. And with this £10 million, we've built a bunker with a gun and an accelerator system going up to 6 MeV. And this will feed some enclosures in which experiments can be done. It turns out industry is prepared to come here and use this facility and has done already. So that gets us the brownie points for helping industry. And I'm not cynical about it. I mean, it's important that we help industry. It's important we have these collaborations. But this beam could be taken on through here into what is really our real ambition, which is something called Clara. And the idea is to put on the end of that presently funded and operational, VELA is operational, it's actually been running, to put this new system, compact linear accelerator for research application, on the end here. As you can see, it's a LINAC based system. It goes up to 250 MeV. It's got seed lasers on it. It's got highly focused things. It's got a lot of radiation devices. It's got a lot of superconducting LINAC in it. In other words, all the technologies which are relevant to the next generation of anything in advanced accelerators, with particular emphasis on short pulses. And the beam short pulses will produce very, very high beam instantaneous currents, kilohertz sort of thing. Flexible beam parameters. The FEL test facility will probably be in this region, this wavelength regime here, which matches the seed diagnostics availability. So it's for general accelerator developments. If we can get that project, that would be fantastic. But it's not yet funded. But it has been, bids being put in as we speak. I'm not going to waste a lot of time going through it. You've got it in your slide, in your pack. But this just shows you the various technologies. Not that you would necessarily work on a single one of these, but all of these will be relevant at some level to every single accelerator project. Some more important than others. Magnets, RF system, etc. But don't forget all these other things, like all the engineering, the process control, the radiation losses, various things which make up real accelerator projects. And the emphasis therefore is on multidisciplinary teams. I'll come back to that point I made this morning to you. I personally believe it's very important that you have a broad-based education. So when you attend these project meetings, you understand what everybody else is talking about. You don't just understand your own thing that you're doing in a specialised manner. You can join in and influence the decisions of other people just by intelligently understanding things and listening to what they have to propose. So I think I would urge you to emphasise that in your own careers. So this is the Cockcroft Aztec programs. Not all of these are very active, but they've all been very active in the last 2 or 3 years. These aren't things from 10 years ago. These are relatively recent. So we've talked about particle nuclear physics. There is a very active program involvement with the LHC and with upgrades that we talked about. Neutrino Factory, I think, is probably going to flatten out a bit. I'm not quite so sure how much future money there will be for neutrino in the short term. CLIC is very much part of this next linear collider, But importantly, it's about the collaboration between the Institute here and CERN, which is very strong now. There are collaborative formal agreements between CERN and Cockcroft for collaboration. And so that's something that most people will find relatively easy to join in with. We've looked at Emma. Emma may well not have money for running in 2 years' time. We're fighting every year to get enough money to turn it on because we've got to fund it from our own resources. Alpha is a anti-proton ring project at CERN. So again, we fall in a CERN-Cockcroft collaboration. Photon sources, we've got ALICE, which is quite expensive to run, unfortunately. We've got NLS, which I've discussed, and Clara. I don't know why Alice is in twice, apologies for that. Neutron sources, we've got the European source, possible ISIS upgrades, I mentioned those. Medical stuff, therapy. I've not mentioned isotope production, but the other area which high intensity proton accelerator could be used for is the production of medical isotopes for diagnostics. Very big topic. Where do all these isotopes come from nowadays? Generally from reactors. Licensing reactors is getting more and more difficult. They really need to be replaced by accelerators because more and more countries are getting very reluctant to license any new reactor, even for research of this sort. This is for medical purposes. We've talked about some of this novel stuff. I've got time to talk about it anyway. Awake is a plasma project with CERN-based technology. Talked about test facilities. Talked about FELs. It'd be a mistake not to mention training. This institute has a very, very strong reputation in training, and particularly training under the auspices of the European Union programs, like the Marie Curie program. And whole areas of training for postgraduates, for example, have been pioneered here and have been accepted Europe-wide by other countries, which were pioneered here on the people at this lab. But the important thing is to align everything to funding agency priorities, because if you don't do that, you're not going to get much money to do your work. I think this is possibly the last slide. It's worth just mentioning. This is a bit of history for you, in case you didn't know it. The Accelerated Science and Technology Centre, ASTEC, was formed in 2001, quite a long time ago now. It was a response to the decline of R&D in accelerators, and before this date, there was very little activity on R&D. None of the stuff that we've talking about for UK and for this institute existed 10 years ago. It was formed in effect in 2004. Cockcroft and John Adams Institute were created, and the university research was refunded after 10 or 20 years of almost no funds. The recognition we needed to fund this work, and we needed to fund the collaboration between a lab like Daresbury and universities. Or RAL, same thing with universities. That multiple HEI collaborations were vital. That universities were too isolated, they needed to do more collaborative work together. And again, it's you people who are going to make this happen in the future by collaborating with other colleagues at other universities. There is a tendency for universities still to be a bit sovereign, a bit jealous of their own area, right up, particularly with senior staff level in universities. So you have to be a bit careful to understand all that. There were some big grants up to 2011. Unfortunately, some of those grants have not been, like the International Linear Collider, which is being parked a bit. We're going to have to look for new topics and areas now. So there's healthy programs. Okay, if we get Clara, this statement will not be correct any longer. If we could get that Clara project, then we will be into new technology, new physics, and be able to do something that nobody else in the world could do. But Accelerator R&D is under continuous review by STFC, which is the principal funding agency. And what is going to be the next major UK project? I don't know. But this is my last slide, concluding remarks. So I hope you've enjoyed a rather broad, and I know it's a bit shallow, coverage of World of Accelerator. I've tried to give you some sort of flavour of what's going on around the world in different areas. And who knows where you'll end up working? You don't know yourselves, I'm sure you don't. One or two of you may have a more focused idea, but I'm sure a lot of you will be just taking it as it comes at the moment, seeing what attracts you. I believe that Accelerated Science and Technology, which is what this acronym is, offers an exciting challenge. It certainly offers a career. It's not just a short-term thing for students. There are whole career posts available in this area. Multidisciplinary and international, if you like that sort of work, which a lot of people do. There are academic projects all the way through to mega projects dominated by big project and big labs. It's up to you which type you want to join, but the whole alternative is available. And just a last plea. There's now in existence an Institute of Physics group. I hope you all join the Institute of Physics. If you've not joined, I can have some sympathy with you, because it took me quite a while to persuade myself to join them in the old days, because they didn't seem very relevant. One of the reasons they weren't very relevant was that until about 4 years ago, there was nothing for accelerator people. Accelerated people would expect us to live within groups headed particle physics. And accelerated physics is not particle physics. It's linked closely to it, but it's separate. We now have a particle acceleration beams group in IOP. Please join IOP. It's a professional body for us all. It influences physics in this country. It has influence on government through physics knowledge. And there is now a group, specialised group, that has regular meetings, workshops sponsored. You'll see them here while you're here. And please give your support to that group. And carpe diem. Seize the opportunities while you're here. That's it. Hope you enjoyed it. And you're going to have some heavy stuff now from now on. Thank you very much. Anybody got any queries, you can ask them. Any questions? Any comments? Anything you think we missed out? Sure, you're going to go away and think a bit about it anyway. Okay. Thanks for your attendance. Thank you. And everybody sign the register, I hope.